In this lesson, we will learn how to identify, model, and assess specific risks, technical and integration problems in a project. This is the most significant risk in this project. We will do this using two alternative approaches to estimate the cost of the risk: direct analysis and incremental analysis. This will lead us to strategies to mitigate it. So we first identify the risk. As we saw in lesson 7.4, we can detect the most significant risks using a correlation tornado chart on cell B8, total cost. In this analysis, the second most impactful factor is the risk of technical and integration problems, only surpassed by the development task. Another way to identify it is through the risk map sheet discussed in lesson 7.5, where this is risk number 7, and it is among the 4 top risks with the highest potential impact according to the 70th percentile. Now, let us explore the usefulness of the RiskX sheet to visualize risks. Select a 7 in cell A2 of RiskX. This risk is linked to task 16. To assess it, we modeled 2 key elements: frequency, the number of times it may occur during the project. It is modeled with a Poisson distribution with a mean of 2. Impact on duration. Each event may delay the task between 2 days as a minimum, 5 days most likely, and 10 days as a maximum, using a PERT distribution. Impact on cost. Each event could cost us between $500 as a minimum, $800 as a most likely, and $1,000 as a maximum, also modeled using a PERT distribution. By combining frequency and impact convolution, we obtain the total effect of the risk on the task. Remember that we saw the concept of convolution in lesson 217. Now we estimate the cost of the risk. The first option is through direct estimation. In the risks sheet, we define cell T9 as an output variable, which contains the total cost of the technical and integration problems risk. Then we simulate the model and analyze the histogram. The result shows that the average cost of a risk is approximately $1,560. This means that any mitigation strategy costing more than $1,560 would not be economically efficient. At the 70th percentile, the cost could reach $2,110, which could also serve as a decision threshold. The second option is through marginal estimation. First, we simulate the model with all risks activated and obtain the total cost with a mean of $29,900. Then we exclude risk 7 out of column D, placing a 0 for this particular risk, resimulate and record the new mean cost of $28,300. The difference between both results, approximately $1,600, is the marginal value of the risk. Now we compare both methods. Both methods may produce similar results, but marginal estimation is more robust when dependencies exist between tasks risks. For example, if there are risk correlations or successor tasks that, depending on a probabilistic schedule, may be delayed, or etc., that is why we prefer the marginal method in complex models where correlations influence the results. So we conclude, risk analysis can be done individually or marginal. The marginal approach is more comprehensive when interdependencies exist. Knowing the expected cost of a risk allows us to evaluate whether it's worth mitigating it and how much to invest on. In the next lesson, we will apply this analysis to design a specific mitigation strategy for this high priority risk.